What I'm going to talk about today is what I've called explicitly ethical agent reasoning. So this is how we implement computational systems to reason explicitly in an ethical manner. And I'll sort of delve a bit deeper into exactly what I mean by that. I want to just, there's this huge raft of names here. This is work that's all been done with a big range of people. Michael Fisher, who was originally my PI when I first got in this area. I was a postdoctoral researcher. Maria Slavkovic, who was on the program committee, and she and a whole group of her students I work with on some of this stuff. Matt Webster, Alan Winfield, who's here, Paul Bremner, who was a PDRA of Alan's, Felix Linder, Martin Mose-Benson, Rafael Cardozo, Angelo Ferrando, and some people who've been undergraduate students doing projects with me, Tom Evans, Daniel Ini, and Christina, who is actually giving a talk in this workshop, so that's really exciting too. So some of this I expect is familiar to people in this workshop. So I mean, I'd say I'm working in the area of machine ethics, and I consider that as how to automate moral reasoning. So there's a lot of talk at the moment about AI ethics, and that's a much wider field and encompasses, you know, lots of things Toby was talking about, social processes, political processes, requirements capture issues. So I'm focusing much more in on sort of one of the technological solutions here. But I think it's important to say that's not because I don't think these other things are important. You know, this is one piece of the puzzle in how we try and make the way computers affect our lives and societies more ethical, but it's not the whole answer or necessarily even the most important part of the answer. Machine ethics, I mean, you know, you can see aspects of it going back a long way, but this paper by James Moore early this century was kind of one of the key papers in really sort of defining what the field is. So it's called The Nature, Importance and Difficulty of Machine Ethics. And he comes up with these 4 classifications of what he calls ethical agents. And I think it's worth, you know, going over these kind of quickly. So you have ethical impact agents, and these are agents that have some kind of ethical impact, irrespective of what they themselves do. You know, seatbelts, in a way, are a really simple ethical impact agents. If you have seatbelts in your cars and people use them, fewer people die and get injured. So there's a clear ethical impact there, even though there's no real ethics embedded in the seatbelt itself. And there are plenty of computational systems which don't, you know, particularly do anything that we could consider ethical in their actions, but their simple existence has made an ethical impact upon society. Then we have implicit ethical agents, and these are the ones that, you know, Toby was advocating towards the end there. They are ethical by virtue of the way that we have programmed them, and certainly lots of these machine learning systems, if you're trying to make them optimize some fairness metric, I would say that those are implicitly ethical agents. They are ethical by virtue of the way that you've trained the network and the constraints you've placed on that training, the things you're trying to optimize. But then this machine itself and the decisions it makes them within that kind of ethical set of constraints. The ones I'm interested in are ones where the machine, in some sense, has to ask the question as part of its reasoning process, is this the right course of action, or is some other course of action preferable? And it explicitly refers to some concepts of good and bad, or right and wrong, as part of that reasoning. I think actually the kind of ethical agent that Toby was saying is, you know, sort of not our business to be worrying about at this point in time, and I'd agree with him, would be these ones that James Moore classifies as fully ethical agents. And the distinction between explicit, well, actually, to be honest, the distinctions between all of these are a bit fuzzy. But a fully ethical agent, the example we have are humans. We operate ethically in a very flexible way. In some sense, we can decide what the ethical course of action is from first principles. It's not clear how we do this, but we are fully moral agents and can be held responsible for our actions. Whereas the sort of explicit ethical agents I talk about, I still feel they embed human values. It's still the responsibility of the programmer to ensure that they are expressing our values, and it is ultimately the programmers or some conglomeration of the programmer, the company they work for, the user, the deployment environment, and the users who are ethically responsible for the actions of that system. The program itself cannot be held morally responsible. Another distinction that gets used quite a lot is top-down versus bottom-up. And in machine ethics, we normally consider top-down to be where we take an ethical theory, typically from philosophy, and we ask how we can implement that in the agent's decision making. So when these explicit ethical agents are trying to make a decision, they refer to a decision mechanism from some specific ethical theory. And usually when we talk about a bottom-up approach, then we talk about an agent that somehow observes what is ethical behavior, or has a training set of ethical actions, and so it learns from data what is ethical behavior. I don't really like this being called top-down and bottom-up, in that the kind of classical description of top-down and bottom-up from computer science is that if you're top-down, you state your problem, and then you break it up into smaller problems until you find something that's easy enough to be solved. And if it's bottom-up, you know somehow what your small problems look like, and you solve them, and then you kind of compose them together into the high-level solution. And I don't think that view maps particularly well onto these two different ways of approaching implementing ethical reasoning, but it seems to be the terminology we've got. And there are definitely these two approaches, and I'm mostly concerned with the first. So that's, I take an ethical theory, usually from philosophy, and I ask how I can actually implement that in the way a machine reasons. And if I'm taking an ethical theory, then there are actually lots of candidates, and they fall into three broad groups. One goes sort of all the way back to the ancient Greeks. So Socrates is standing in for that ethical theory here, and they're referred to as virtue ethics. And sort of in the original expression is slightly circular. The idea is that the ethical action to take is the one that a virtuous man would take. But you see lots of expression of that in terms of understanding that there are certain qualities or virtues or principles, the terminology varies, that you want to promote or avoid. So you ask of a choice, you know, is this the honorable choice? Is this the truthful choice? Does this, you know, those principles Toby had, you know, does this promote beneficence? Does this demote malfeasance? All those kinds of things. So you ask how a choice works in line with some set of virtues. In the middle, we have Kant, and he tended to have quite a rules-based view to ethics. That often gets expressed in when we're implementing ethics by taking some kind of deontic logic and writing a set of rules, and these will be in terms of obligations and prohibitions typically. But I mean, I don't think Kant would necessarily recognize those deontic logic systems as particularly what he was advocating, or certainly not solely what he was advocating. But certainly he talked in terms of often sort of slightly higher level rules, but there are a set of higher level rules that you follow that constitute what would count as ethical behavior. And lastly, we have John Stuart Mill here, who is standing in for kind of consequentialist ethics. And so that's where we look at the outcomes, or perhaps the predicted outcomes of whatever our course of action is, and usually we try and score it in some way. And then we have some way of deciding based on the scores. And the most famous of these is utilitarianism, where we pick the outcome that has the highest score for the most people. But there are actually alternative ways of looking at that. You could, for instance, try and pick the outcome that has the highest score for the person who will come out worst. So you kind of try and have maximize the worst outcome for somebody. So it's like the least worst from that person's point of view. I don't have a name for these two categories, but I increasingly am quite interested in this distinction, which I've called global ethical systems and constraint-based ethical systems. So a constraint-based ethical system is much easier to go with from certainly an engineering point of view. So we assume that not all the reasoning that happens in the system has to directly involve ethics. So the whole system does not have to be an explicitly ethical agent. We place the ethics in some subsystem that can guide or constrain the actions of the rest of the system. And in particular, if you've got something that has been trained on data and maybe is a bit opaque, but nevertheless, you've got experimental data to say that it performs really well, but you can't actually guarantee the ethics, then you can have an explicitly ethical system sitting next to this and in some sense vetoing the actions it makes. In the very early machine ethics systems, Ronald Arkin produced what is often considered kind of the first machine ethics system, and it was a constraint-based system, and it was actually for a missile targeting system. And the idea it was constrain the choices of the underlying targeting system based on the rules of engagement and the laws of war. We also see systems that assume that all choices are ethical. And in a global sense, all choices are. If I choose to drink a cup of coffee as opposed to not drinking a cup of coffee, well, at some point embedded in my choice of a cup of coffee is the whole global infrastructure about how coffee is farmed and produced and delivered to my kitchen. So there is an impact that is ethical in my choice of beverage and when to have a beverage. But in an engineering point of view, if you try and make ethics a part, the kind of fundamental decision mechanism in your system, it gets very difficult. And you do start saying that, my choice, the robot's choice to recharge itself is an ethical choice. And that seems also, I think, quite counterintuitive. And part of the reason we want to do explicit ethics, or at least part of the reason I want to do explicit ethics, is that it lets you talk to stakeholders about what their values are and map them quite closely to what's happening in the way you've implemented the system in the machine. And if you start telling them that, whether the robot's on full charge is an ethical choice, well, that doesn't work very well in terms of requirements and people's understanding of ethics. But I think it is true that all decisions have an ethical impact. And so you can try and have your ethics taking part in every single decision that's taken by your system. Yes, taxonomies are hard. So I've just talked about a whole load of ways of categorizing systems, categorizing ethical systems. And I think it is very useful to think in terms of these categories. They help us understand what we're talking about. But you can get, especially as computer scientists, you can get very obsessed with trying to work out precisely what the definitions of these categories are, so that anytime I come across any particular system, I can very precisely put it in a particular box and say it's one of these and it's not one of these. Sadly, the world doesn't work like that. And it's perhaps better to think of these things all in terms of features a system exhibits that may be more like one and less like another, but it could have features that seem to kind of be part of both. So for instance, when I say a system explicitly considers the question of right or wrong, well, what do we really mean by that? What's the difference between something like compass, which is saying, do I think this person is likely to offend or not likely to reoffend? Because that we could see as a decision about right and wrong. It's making a decision about the likely cost of releasing this person to society, which is an ethical decision, compared to a system which is saying, well, is this the best decision according to Kant's categorical second expression of the categorical imperative, something like that. So it can be quite hard to figure out where the lines draw. Lots of these deontological theories involve reasoning about the intentions of the agent when taking an action, and that seems to have something of a virtue ethics, its flavor. Were they intending right or wrong? Was this a kind of thing that a good person would do? And what if we have this top-down design of our reward function, which we're training a system? So we're not just looking at what people are doing and getting someone from mechanical to say, yes, that was the right thing, no, that was the wrong thing, and then training lots of data, which people have more or less actually suggested. It seems to me like a horrific way to decide to try and train a machine to be ethical, but there you go. But maybe you could have some kind of top-down design of your reward function, drawing on some kind of ethical theory, run lots of decisions through it, use that ethical theory, the reward function, decide if they were ethical, and then train them to the machine to choose. And then it would have a kind of top-down, bottom-up flavor. So I think they're useful for talking about things, but don't get too obsessed with trying to decide precisely which box any particular system fits in. So going back now, I've spent lots of time sort of setting the framework within which I think my work fits. The very first time we got involved when I was working for Michael Fisher with this kind of explicit ethical reasoning was following on with some work that Michael Fisher and Matt Webster had done with the Civil Aviation Authority in the UK. What they'd been trying to show was that it was possible to program an agent guiding an unmanned aircraft so that it would obey the rules of the air. And the rules of the air have a whole load of things. The one they liked best was there was a rule which said that if you were in a head-on collision with another aircraft, you should turn right. So the idea was that if two aircraft find themselves in head-on collisions, they'll both turn right and they'll miss each other. But there was another rule that said that if there's an obstacle in the vicinity of an aerodrome, then you should turn left. So these two rules seem to be in contradiction to each other. So they had some fun showing that these rules weren't consistent. But anyway, they programmed up an agent so it would obey the rules of the air. They demonstrated this to the Civil Aviation Authority. And the people in the Civil Aviation Authority said, yes, but what if you're supposed to break the rules? And it turned out that they had a kind of implicit rule, was that they understood that a human pilot would always disregard the rules of the air if it was necessary to do so in order to save human lives. So they hadn't felt the need to explicitly say this. It was just embedded in their reasoning that there are situations that arise when the rules of the air would clearly be going to cause a crash. For instance, if you're doing this turn right, but for whatever reason, the oncoming aircraft, the pilot isn't obeying the rules of the air, and you get into this kind of everybody's turning the same way, well, maybe you should turn left to try and, well, he's clearly turning left, maybe I should turn left too, and then we won't have a crash. So this was sort of embedded in their understanding of how the rules work. And since then, I have a PDRA at the moment called Joe Collinette. He's looking at the highway code in the UK. And he says, actually, it does explicitly say in the UK highway code, this is how you drive on roads, that all the rules can be broken if it would be safer to break the rules than to follow the rules. So they have this kind of get out, which is if there is an ethical override, then you should take the other choice. So we became interested in trying to express how you decide in these situations what you should do. So this was a kind of ethical reasoning as fallback. It was, if for some reason the rules of the air are not telling you what you should do, what should you do instead? And Maria did quite a lot of work with us on this. So we had this architecture, and let's see, where's a good place to start? We're working with something called the Beliefs, Desires, Intentions Programming Language. So it selects plans of actions based on its beliefs about the world and the goals it's currently trying to do. So let's start in the middle here, where it says you've generated a set of plans. So you're in some situations, you've generated a set of plans. And the first question is, are there any plans for this situation that you've not yet tried? If so, then you get a new plan, and you from your planner, and this is an implicitly ethical agent, this planner. It has a whole set of plans. We assume someone has engineered these plans, that they obey the rules of the air, and they are ethical in some sense, and the system doesn't have to worry about that. It gets the new plans, and it tries to execute them. It selects one, the most ethical, it starts executing that plan, and it sees if it works. And if it has, it doesn't need to do anything. And it goes around this circle. But at some, okay, sorry, it sets some plans. I'll start again because I get myself confused. You get a set of regular plans in the planner and you try all those first. And if they're not working, then you go to your ethical planner and you try and get some new plans which are not from those which have been pre-constructed for you. And so this might be some machine learning system, it might be some random route planning system. These plans may not obey the rules of the air, but since all the ones that do obey the rules of the air aren't working or are predicted not to work, you pick one of these new ones and then you use ethical reasoning. So the bit in the dotted box is your exceptional reasoning where you actually bring in the explicit ethics. So it's only if your ones that have been your implicitly ethical plans are not working, you then go to this explicit ethical reasoning. So what does the explicit ethical reasoning look like? So this is based on an ethical theory called prima facie duty. So Maria kind of set an expression with them, did some work kind of operationalizing those for us. So we have a set of ethical concerns which we rank. So we say, you know, killing is worse than stealing, and stealing is worse than lying, and so on. And in fact, we start with high-level ethical concerns like killing, stealing, lying, and then we instantiate those in a domain-specific way. So this is a bit like looking at those ethical principles Toby had for medical ethics, which are things like, you know, respect autonomy and justice, but you instantiate them for a situation where it's like, you know, respecting autonomy means have you asked the patient for consent? So you have these kind of lower level principles which relate to the higher level principles. And we said that a plan, P1, is worse than another P2 if P1 violates an ethical concern and P2 doesn't. So if P2 doesn't violate any of your ethical concerns, go with P2. If they both violate some of your ethical concerns, then if the worst concern violated by 2 and not by P1 is less serious than the worst concern violated by P1 and not P2, then you want to pick P2. So the idea is they both violate concerns, but you know, P1 is going to kill someone, whereas P2 just involves lying to someone. Well, if those are our choices, we'll go with lying to someone rather than killing someone. And lastly, if the worst concerns are equally bad, so they all involve doing, you know, equally bad things, but P1 violates more concerns than P2 does, then we go with P2. So if we're going to violate lots of ethical concerns, we might as well violate as few as possible. So we set up some scenarios. So we had some ethical concerns, and this is a situation where an aircraft hasn't even left the ground, it's taxiing on the runway. There are a surprising number of rules in the laws of the air about taxiing on runways. So we had these ethical concerns. So we said the most serious, that's 5.4 there, is not to collide with a manned aircraft. And that's because this is likely to, you know, damage the aircraft and kill lots of people. The next most serious is do not collide with people, then don't hit any airport hardware, and lastly, don't damage this aircraft itself. Remember, this is an unmanned aircraft, so it doesn't have people in it, so we're not worried about passengers or crew. So the scenario is that the aircraft is taxiing on the runway, and its brakes have failed, and its options are to turn left, where it will damage the aircraft and airport hardware, to turn right, where it will damage the aircraft and risk colliding with some airport workers who are, you know, on that side of the runway, or if it carries on, then it risks colliding with the manned aircraft in front that is waiting on the runway to give them permission to take off. And so the idea is in this situation, it will choose to turn left, because although that violates 2 concerns, they are not as serious as colliding with people or colliding with a manned aircraft. And we had, you know, several scenarios, some a bit more complex than this. But the idea is at this point, it has to leave the runway, which would be violating the rules of the air, or some of the options involve leaving the runway. So it tries to use the ethics to decide which of these options to pick. All the work I'm going to talk about, we implemented in something called the MCAPL framework. That's model checking agent programming languages. And all the examples are still in that framework, and they all run, or they're running 2 months ago, last time I ran all the tests. So if you're interested, you can download this, you can look at the examples, you can play with them. So there's this model checking thing in the title of the MCAPL framework. And one of my other interests is verification of programs. And the model checking agent programming languages framework gets used quite a bit for modeling one of these beliefs, desires, intentions agents that is controlling an autonomous robotic system of some kind. And the way model checking works is you can think of it as exhaustive testing. There's some clever stuff in there, but I think it's easiest if you've not come across it before, just imagine it as exhaustive testing. And obviously, if you've actually got a robotic system, well, there are so many possible states in the real world. You can't exhaustively test over every possible situation you might find it in. So we put a box around this beliefs, desires, intention agents. So what happens is data comes in from sensors, and we abstract that into beliefs or facts about the world. So we abstract it into some kind of abstract description of the situation you are in. And there are a lot fewer abstract descriptions of the situation than there are actual situations. So we are going to exhaustively check over all those abstract descriptions of the world. The agent makes some decisions. So this is a very simple example. The abstract descriptions of the world are either there's an obstacle in front of you, or you can see a path, or neither, or both. Those are the kind of 4 situations you can be in. So it has some kind of ultrasonic sensor that is detecting an obstacle. It has some kind of line following sensor that can detect there's a path. And it has this plan. If the agent believes there's an obstacle, then it will try to stop. It probably also has a plan. Yes, and it also has a plan. If you believe there's a path, then you should follow it. So it takes the situation of the world in, it applies one of these plans, and so then it will either stop, or it will try and follow a path, or it will do nothing. And this goes out to some control system, which then handles actually executing that. And for instance, following a path, any of you who know a bit about robotics, there's a whole load of, you have 2 sensors or maybe 3 sensors, and depending on whether you can see the path with which ones, you'll turn one way or the other. So there's a whole load of computational stuff there, but the agent's not concerned with that. It's just said follow the path. So what we want to verify, if the agent believes there's an obstacle, then it will stop. That's our safety consideration. And in this case, it's really simple. There's 4 options. You just check each of those 4 options, and you see which command is sent out by the agent. And depending basically on the priorities of those 2 plans, it will either stop or follow a path. And the only really interested one is where there's both an obstacle and a path. It's kind of which of those 2 things will do. Obviously, we normally apply this to rather more complex problems. And to be honest, typically the errors we find when we do this kind of model checking are these edge cases where lots of things are happening once. It's there is an obstacle and a path. And in those sorts of situations, it may be people haven't thought quite carefully enough about the priorities of their plans and which ones will apply, or there isn't a plan at all, but something does need to be done. And then that's the kind of error you find by doing this model checking thing. So we have this model checking framework, and we tend to apply that to these explicitly ethical agents that we create. And I can see I'm running short of time. So in that aircraft example, we did a couple of different things in terms of how we set up this exploration of the space. We had plans that didn't particularly do anything, but we were annotating them with which of the ethical concerns were violated. And we explored all combinations of the ethical concern annotations and basically checked that the aircraft always selected the least unethical choice according to that theory that Maria had come up with. We looked at this case where we had a fixed set of plans with a fixed set of consequences, e.g. it could land, this was an emergency landing, it could land on a road that would damage infrastructure, it could land in a field which would hit some cows, but we varied which plans were available. And we would check the aircraft only landed on a road if there were no field available to land in. And that should be no empty field. If there were cows in the field, that would have changed the ethics a bit. And we also had a fixed set of plans and consequences, but varied whether they succeeded. And in that case, we had this idea of a collision with another aircraft and whether the other aircraft was obeying the rules of the air or not, and could the system actually detect when that was happening and therefore try and pick the plan that was going to break the rules of the air but avoid flying with the aircraft. And so we've got this system where we have this explicit machine ethics encoded up according to some theory, which is supposed to embed human values. And we do get a bit into what do we actually want to prove about this. And obviously we want to prove that the system always does the right thing. But that's much too vague if we're trying to do verification or formal verification like this. We need a more precise property. And most of these systems will have a set of rules or a set of utilities if it's some kind of consequentialist system. So it's like, killing is worse than lying, but that will be expressed as utilities of outcomes, and a decision mechanism. And particularly, these decision mechanisms are often geared towards how you decide dilemmas. So in theory, because you've programmed your system in this very explicit way, so it's not a deep neural net, you can show people your decision making, and you can show people these rules and utilities, and they can sign off. They can say, yes, those capture our values. That is how we want the system to reason when ethics is on the line. And so if we let people sign that off, there is a kind of question, well, what is there to prove? We have directly encoded what the requirements in the system. So I'm going to tell you why, obviously. So this is an example of some work I did with Martin Mose-Benson and Felix Lindner. And they had one of these global ethical reasoning systems, but it could reason with a variety of different ethical principles. And so you could switch them around. So we came up with this abstraction of this. And this is an ethical reasoner, is a system which uses an ethical encoding of some kind to recommend or allow some action or set of actions given some situation. This is quite a vague description, but we were trying to describe quite a large class of things. So formally, we represent situations as sets of formulae from some language L, and ethical encodings as a set or type EE, and then actions as a set A. So an ethical reasoner takes a situation, some kind of encoding, and some kind of set of potential actions, and returns a set of allowable actions. Or it might be just one. In the case of utilitarian, it picks the one with the highest score. But some of these allow a set of actions, and you could pick one at random, or you can have some kind of other decision mechanism. And our actual particular interest was as contexts changed. So our argument was that it's quite hard to have one ethical encoding that applies to all situations. You actually want a set of them, and you want to change them as the situations change. And this is for sort of engineering reasons. There's no reason in principle why a perfect reasoner can't have one encoding. And we had this context specification. So phi is a formula that describes a situation, and we can switch our ethical encoding as our situations change. And we embedded this in something in the MCAPL framework. So we called it JUNO. So here was the system that Felix and Martin had developed that could reason with a particular ethical encoding. And we embedded it in this cycle, which is quite like beliefs, desires, intentions, agents, though not quite, where you perceive the world, you do some inference. If you needed to update your encoding, you would. You'd then send your actions to the hero agent and ask it to send you back one or some subset. You pick one of those, you do it. There was a bit of housekeeping clean up, and you went round this cycle. And so the example we were looking at was a smart home, and one of the ethical decision mechanisms we were looking at was the principle of double effect, which actually goes back to the Middle Ages. And the principle of double effect says that the net balance of consequences of an action must be positive, and no negative consequences can be intended. And to be honest, I find it really difficult to figure out what we mean by a computer system to intend something, but they had an encoding of that in their hero system, so we went with that. Something was intended even if it wasn't the end result of what you were trying to achieve, you had to do this thing in order to get to the point where you wanted. So I had some utilities, and this was how we were going to calculate net balance of consequences. So I said in this smart home, if the lights were on, there was a small negative utility because obviously it's using up resources. If people leave the house or are forced to leave the house, that's a negative utility because it causes disruption. If people are safe, then that's a big positive utility. And whether people can see, that was 0 or 2, depending on context. So the idea was at nighttime, people don't need to see because they're all asleep, but during the day they do need to sleep, so they depend on the context. And then we had these things called mechanisms, which were how the system would reason about what it should do, and the effects of what it could do. So, if it turns the lights on, the lights are on. If it's lights on or it's daylight time, then people can see. If you need to do an evacuation and people can see, then they will leave the house. If people leave the house or there is no danger in the house, then the people are safe. And if there's fire, then there's danger in the house. And I actually programmed this up in such a way, well, I wrote this program essentially, that if the house was on fire and it was nighttime, it wouldn't do anything. And I spent a long time trying to work out why it wouldn't do anything. And the reason was that in order for people to leave the house, the lights had to be on. So that was an intended consequence of turning on the lights. And that has a negative utility. So according to the principle of double effect, one of the intended consequences was negative, and therefore it was ruled out. And so the system would not turn the lights on, even to let people get out of the house. Now Martin, who's a philosopher, said that I had misunderstood the philosophy here. So I got it wrong, but I had spent a long time looking at this because I didn't really understand how the principle of double effect worked, to try and figure out what was going on. So even with something here, which is 4 utilities and 5 rules, it's quite easy for a stakeholder to say, yes, that captures my values, and not realize what the consequences of that encoding are. And those consequences may not capture their values. So in terms of the sort of properties we might want in an ethical reasoning system, we can do verification to check the underlying decision-making implementation is correct. And that was this kind of, I don't know if you remember, the very first thing I proved about the aircraft was that given some sort of anonymous plan, it would always select the least worst according to the theory. And that's really just, have I actually implemented the decision mechanism from philosophy that I claim to have implemented? And that's always worth doing some kind of verification that this underlying implementation is right. And then I said you can check sanity checking properties. So, there's a property that if there is a fire, the house will always evacuate. Now, in a way, you'd think, well, that is one of your overriding ethical rules, but you can check that really always happens, given the whole set of rules and utilities or whatever that you may have in the encoding, that one is always getting the priority. You might be able to express that some of these ethical values are also legal ones, and you might want to check that the legal ones are always obeyed, even if these other ones are going on. I mean, obviously, I've just been through a whole lot of examples where the legal ones have an implicit get out of if there's an ethical override. And of course, it's well known that legal is not the same as ethical. And you can do what I call scenario programming. You can set up a particular scenario with some random elements in it, and check that your ethics are always doing what you expect in that scenario. So if you give people a scenario, they can tell you often what they think should happen, even if they can't articulate it in terms of some kind of philosophical theory. And so you can use that scenario programming as, again, a kind of sanity check to check that you really are capturing the values of the stakeholders. We're running out of time. So I've done a lot of this kind of work where I've taken an ethical theory and I've implemented it in some way. We've used something called probabilistic model checking to assess the risk of violations of theory. So a lot of the kind of stuff we've done is a kind of yes, no, it always obeys a theory or it never obeys a theory. But obviously there are situations where you might want to say, well, how often does something bad happen? And I did that work with Alan Winfield, among others. And with an extension of that work, we looked at connecting an actual robot which had a Python-based but still beliefs, desires, intention library, and an ethical black box, which is something that Alan advocates. So it was recording all the ethical decisions being made. And we had this kind of ethical governor. And that governor could generate alternatives. So it wasn't simply vetoing actions. Sometimes it would say, none of these actions are good enough. Go away and think of some more. And that was partly because there was a very large search space of options that the robot could take. And so the underlying system was limiting the exploration it did when it suggested things. There's a framework for what we call multiple evidential reasoners. And that's when, particularly if you're in some kind of virtue ethics-y type situations, it's like, well, how do you know there might be a privacy violation? How do you know if there's going to be a safety violation? How do you know if there might be a violation of human autonomy? So you have to have some systems to actually even determine that these things are a case. And you probably want multiples of these systems with the different ethical concerns or principles that you're interested in. Christina will be presenting later in this workshop how we might use the feasible logic as a way to sort of simplify what you present to the stakeholders. So, you might have rules that generally hold, and sometimes you have some exceptions to those rules, and you want to kind of separate the general rules from the exceptions, and Christina will talk about that. And also, Maria Slavkovic and I have grappled a bit with the question of how you benchmark an ethical system. So you get a computational system that claims that it is implementing ethical reasoning, and you have another one, and these can look really different to implementations of explicit ethical reasoning. How might you actually compare them, benchmark them, describe what their properties are in a way that isn't just, well, I took some examples that suited the particular theory I was interested in, and it works on those examples, which is what is happening in a lot of, if you look at papers about explicit machine ethics, you'll see that's what's happening in a lot of those papers. Looking forward to kind of work I'm kind of interested in doing in future, ordinary people, you and me probably, don't use a philosophical ethical theory framework very often when we try and decide what to do. I very much doubt you regularly try and weigh out the utilities, the outcomes of your actions, or think about think about virtue ethics or the principle of double effect when you try and decide what to do. Nevertheless, I like to think that most of us function as fully moral agents. So there is a question, are these philosophical frameworks the correct approach for practical ethical reasoning? Lots of them are designed to try and figure out really thorny, difficult edge cases, but in the day-to-day process, is this really how we want to be doing ethical reasoning? So we teamed up with some philosophers here at Manchester, and we're hoping to explore the concept of responsibilities as an alternative to ethical frameworks. And apparently this is feminist ethics. I did not know that, but there's a psychological theory about how men in general reason about what's the right thing to do, and women in general reason about what's the right thing to do. And apparently women in general think a lot more about what their responsibilities are and who they are responsible to and how those things all interact. So we're going to explore that as a way of generating ethical action. And I'm also quite interested in reasoning about how risk and uncertainty interact with all these approaches. Because philosophical theories in general, they like to, as philosophers, and I mean this in the nicest way, try to simplify things down. So when they're looking at an ethical theory and they're asking about what it does, they create a thought experiment where all outcomes are certain. There's no sense of, well, this might happen, and this might happen, and this is unlikely to happen, but this is really likely to happen. And you just, the moment you encounter the real world, risk and uncertainty come in. And I'm hoping to persuade Christina to look at that in future, but we haven't quite got that all sorted out yet. So some open questions, I think, there's practicality, both about the kind of, if you're doing explicit reasoning, what's the complexity here when you're really encountering an open world and a complex situation, and the knowledge engineering of this kind of approach. As I say, you want to have some set of utilities or some set of rules, and your stakeholders need to sign them off. But in a real situation, a real deployment, how easy is it to knowledge engineer that? There are some clear questions about these ethical encodings and how you identify the stakeholders in the system. And that goes out to this wider AI and ethics question, is have you really asked all the people who might be affected by an autonomous system what they think about that system and what it's going to do and how it's going to do it? Most of these systems only look at a single action at a time. So in a particular moment of time, they decide whether a proposed action is ethically acceptable. It'd be quite interesting to look at what happens over sequences of actions that are proposed. And the interaction of multiple agents and how their interactions might lead to results which might or might not be unethical. Resolving pathological edge cases, I mean, that's what a lot of the philosophy has looked at. But there's a question of how often do pathological edge cases actually arise in practice. And so these are things like trolley problems, but nearly all philosophical ethical theories, you can find an edge case where you can say, well, that clearly has made the wrong decision, even though it's in accordance with the theory. So understanding what you do about those if you're implementing all these theories. This idea of the evidential reasoners, the multiple, how do you know if there's going to be an autonomy violation? How do you know if there's going to be a privacy violation? That is non-trivial in my opinion. And I'm not sure we've got good stories about how you get the information necessary to even start doing this kind of high level explicit ethical reasoning. And the benchmarking thing I touched on, work I start with Maria, but there's so many open questions there. It's so difficult to figure out how you even might start doing this big open thing. So thank you. Are there any questions?